Hello everyone, and welcome back to this series on intermediate statistics. Today we're going to be talking about a very important topic known as time series analysis. Now, I'm only going to be doing an introduction to time series today, but I want to sort of illustrate some of the differences and nuances that time series has compared to that of regression. So first off, what is time series? So a time series is just a series or sequence of data points. Our data points are going to be commonly represented by y of t. Some people will use s of t to represent stocks in the financial realm, indexed with respect to time t, right? So this is the important thing here. Time is going to be our, in some sense, predictor variable. Now, with regression, usually we do not have predictor variables that are associated to time, right? But if we were to pretend that time t is a predictor, then one could say, well, couldn't I just fit a regression model to this? For example, I could fit a line of best fit to this via least squares, or I could possibly even fit a polynomial regression of best fit, because according to this graph, maybe a polynomial probably would fit a lot more better. And I'm going to be like, okay, I can use this cubic polynomial to predict the stock value at any time t. Right? So a natural question you may be asking, can time series data or time series problems be solved via regression? And the answer, take a guess. Technically, no, but practically, yes. Keep in mind, we can use wrong things and get accurate models in the end, right? So if this trend for our time series does continue in this way, then it's possible that our polynomial model or polynomial regression model will predict the time values correctly, or the stock values correctly at future times, right? But technically speaking, y doesn't depend on time. Y is just observed through time, right? So that's why it's technically no, but practically yes in some degree. So let's just state out a couple things that we're going to be looking at here. So in regression, what are we trying to do? Well, we're trying to predict y at some particular value of x via some constants beta 0 plus beta 1x, and usually we have this difference term or error term, usually called a residual in regression, called epsilon. Right? So what does this exactly do? Well, it assumes you could do quadratic, but generally we start at linear, dependency or correlation between x and y. That's the assumption associated to regression models, that assumes that there's a linear dependence between them. But in the realm of time series analysis, so time series, what we're going to do, we're going to be trying to predict y with time, and obviously there could be some constants, beta 0 and beta 1, let's call it t, plus epsilon. And the main difference, at least on the surface, between time series and regression, it only assumes, or it only will assume, that y was observed over time. So time series will not assume that y depends on t. It will assume that y has been observed over time, but it's only going to be analyzing the difference in y values and how the y's are changing over time, not with respect to time. All right. So let's just state formally these couple of important things. So variables, for example, y, do not depend on time. They are only observed over time. Right? So let's just do brief, descriptory example. Let's assume that Y represents stock prices for some company, for a company. So what does Y depend on? Well, Y depends on, for example, GDP of the company for which it resides. It could depend on uncertainty. It could depend on price of bonds. It could depend on competition. It could depend on inflation. It could depend on interest rates. It could depend on politics. It could depend on so many things, and so many things are hard to model over time. Or maybe we couldn't get data that's uniformly distributed across all categories at all particular times t, right? So instead of measuring a bunch of different variables, usually it's easier to just look at one variable and keep track of how that variable is changing over time. So time series analysis does assume a more simplistic nature in regards to data collection, but it obviously is going to come with a price because there are so many variables that could be contributing to those residuals and a change of those residuals that these predictions might not be super accurate. And that's technically one of the downsides of time series, but don't worry, there's plenty of advanced time series methods that can be used to predict the value of Y at a particular given time t within some margin of error. Now let's start building a bit of the theory that we're going to use to build our very first time series model. So the first thing that we definitely need to understand is the residuals in the realm of time series. So in the realm of time series, we usually do not call epsilon a residual, we usually call it noise, because that residual, or noise, is commonly caused by uncertainty, emotions, volatility, and several other things. So obviously, every time we make assumptions, we're probably building a parametric model that's not really applicable to every single time series data set, but nonetheless, it's a good starting point to start the conversation. So we're going to be assuming a few things about the noise random variables that is sort of reminiscent for other things such as linear regression and ANOVA. So the assumptions are going to be as follows. So assumptions for our noise random variable. So firstly, let's assume that ET, or epsilon t, is a sequence of random variables that satisfy the following elements. First, the expected value of our noise random variable will be equal to 0, and let's assume that this is true for all time t. Let's assume that's true for all time t. Now, obviously, this is not necessarily the case for all time series models, but we're going to assume this for now just to keep things basic to start the conversation. The second conversation, there exists a number, which I'm going to represent by sigma squared. That's going to be a non-negative real number. Usually it's positive, but technically speaking, it could be 0, such that the variance of this noise term will be equal to sigma squared. And again, this needs to be true for all time t. Right? So it's very important to notice that the expected value of this random variable is 0 for any time, and the variance of this random variable is equal to sigma squared, and this is obviously independent of time as well. For any time t, it's equal to this constant, like 5. Now, before I list out the other two assumptions, I just need to make a theoretical point about this particular expression. So note that the variance of a random variable can be represented in terms of its second moment minus the mean of that random variable squared, right? So variance is equal to second moment minus mean squared. So this is one of those fundamental properties of expected value and variance in their connection. So what does this mean? So we don't know what the second moment of our noise term is, but we do know what the first moment, aka the expected value of our noise term is. We are assuming that that's going to be equal to 0. So notice that we have that this is just precisely equal to the second moment. So the variance of this random variable must be equal to the second moment of this random variable, and we're assuming that the variance is equal to sigma squared. So that means under these assumptions, this is also equal to sigma squared as well. So under these assumptions, if we assume that the variance is constant and equal to sigma squared, the second moment of that random variable is also equal to sigma squared as well. So that's actually pretty nice. The next property that I want to assume is that this random variable is a normal random variable for all time t. And therefore, by properties 1, 2, and 3, we can say that epsilon t is a normal random variable whose mean is 0, and its variance is sigma squared. And that's again for all time t. And the fourth assumption that we're going to assume, take a guess of what this assumption is going to be, is that epsilon t1 and epsilon t2 are independent random variables for obviously t1, not equal to t2. So on the calculation end, what does this mean in terms of the covariance between them? So let's just go through that. So the covariance of epsilon t1 and epsilon t2 will be what? So by definition, that's going to be equal to the product moment, expected value of epsilon t1 times epsilon t2 minus the product of first moments, the expected value of epsilon t1 times the expected value of epsilon t2. And what do we have? Well, if they are independent, then the product moment is equal to the product of first moments. So that means this first term is just going to be equal to the expected value of epsilon t1 times the expected value of epsilon t2. We know that's equal to 0, we know that's equal to 0, and we know that this is going to be equal to 0 times 0 minus 0, which is also equal to 0. So we have that the covariance between these is equal to 0, and moreover, you can say that the correlation between epsilon t1 and epsilon t2, which keep in mind is equal to the covariance of epsilon t1 and epsilon t2, all over the standard deviation of epsilon t1 and the standard deviation of epsilon t2, standard deviation of epsilon t2, and that's going to be equal to 0 over something, which is obviously going to be equal to 0, right? So independence implies correlation equal to 0, but keep in mind it does not go the other way around, right? So these are going to be the assumptions that we're going to be making for these residual terms, epsilon. The next topic that I want to introduce before we build our first time series model is what a moving average is. So if we look at time series data, it's typically not very smooth. So I want to formally state that here. So time series data is not, or are not, usually smooth. And this is likely due to our epsilon terms because they are random variables, which causes things to randomly go up and go down. So one thing that helps smooth out this rocky process is moving averages. So moving averages help to smooth out the data, which also helps us figure out any underlying trends. So if we look at 2 points at a time, for example, we can consider those 2 points, and then those 2 points, and then those 2 points, those 2 points, and those 2 points, we can look at the average of those 2 points. For example, we can look at that average here, that average here, that average, that average, that average, and so on, right? So what I can do is I can define this average as the moving average from time 1 and time 2. I can define this point as the moving average from time 2 to time 3. This is the moving average from time 3 to time 4. I can define this to be the moving average from 4 to 5, and this from 4 to 6. So notice that I'm only looking at intervals 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to that last point in order to get these points 1, 2, 3, 4, and 5, right? So this point is associated to this interval, that interval, that interval, that interval, and that interval, and so on. So if I look at this time series from only looking at those moving average points, notice that I get a relatively more smoother graph compared to the original a lot more rocky looking time series data. So what I can do is I can define very easily the moving average approximation to my time series at time t is equal to t by only looking at one point in the past, and hence 2 points. So it's obviously going to be equal to yt, the point at time t is equal to t, and then the point before, t minus 1, and then divide that by 2. And keep in mind, this is going to be for t is equal to 2, 3, 4, 5, all the way up to m. And you might notice that this is similar to a derivative, I guess you could say. So reminiscent of backwards differences. Since we're always marching forward in time, using backwards differences is typical the way to go, and we can always increase the order by looking at a lot more points in the past. So for example, if I want to look at 2 points in the past, which means I'm going to be using 3 points, I'm going to be looking at t minus 1, and also t minus 2, and then dividing that by 3. And this would be for t is equal to 3, 4, 5, up to m. Right? So that's looking at, so this is looking at interval t to t minus 1 and t minus 2. So it's looking at those points there. And I can increase this to an arbitrary value. For example, I can look at it as order qt. So this is going to be equal to yt plus yt minus 1 plus yt minus 2 all the way down to. So note here that 2 ends at t minus 2. So that means q is going to end at t minus q. And that's going to be divided by q. So we have this expression. And this is going to be for t is equal to, keep in mind, MA2 starts at t is equal to 3 for its domain of definition, so it's plus 1. So this is going to start at q plus 1, q plus 2, all the way down to m, where n is the number of points that we have observed in the past. And this is what we refer to as a qth order moving average. Moving average approximation to yt, where these have already been observed. All right. So now that we know moving averages and a couple of the definitions of what a moving average is and what it aims to do, and we also know a couple, or we have already taken a few assumptions about the noise term epsilon, now let's build our first time series model. So the first model that we want to build for time series is known as the moving average process, and it's built on these two fundamental questions. First, should each of the YKs be weighted equally like we did with moving average? The answer for this is probably no, and we typically don't know YK in the future, so how can we use those formulas in the first place? And if we don't know YK, could we build YK from our noise terms, epsilon k's, for which we've already made assumptions on? And the answer is obviously yes. So the first order moving average process, so the first order moving average process, for which I'm going to just abbreviate by MA1, for moving average order 1, is going to be of the following form. So we're going to assume that yt can be represented as a plus b epsilon t plus c epsilon t minus 1. So obviously, we're going to be looking at the noise term at time t, which is going to be the term that we're associated with. And we're also going to be looking one step in the past. One step in the past. And it's possible that this has some coefficient, let's call it c in front. And we would like this model to be true for all t, for all time t, right? So we can use the same numbers a, b, and c for all time t for which we want to predict in the future. So let's see if we can build a couple things here, right? So we already know that epsilon t is a random variable, epsilon t minus 1 is a random variable, so y of t is obviously going to be a random variable as well, so it has a distribution, it has an expected value, it has a variance. So let's go ahead and find the expected value of this object. So the expected value of yt is going to be equal to what? So that's going to be the expected value of a plus b times the expected value of epsilon t plus c times the expected value of epsilon t minus 1. So we already know by assumptions that the expected value of epsilon t and the epsilon t minus 1 are both going to be equal to 0. So we're just going to be left with the the expected value of a, which is just going to be equal to a by properties of expected values. So we just have this particular expression. So that's actually pretty nice. So for notation, since a is just a random letter, I'm actually going to be notating this letter by mu. So mu is going to be the new name for that constant in front of our MA1 model. Now let's take a moment and think about what this b epsilon t term is and what this c epsilon t minus 1 term is. So the b epsilon t corresponds to the effect of noise at time t on yt, right? So b epsilon t is the effect of noise at time t on yt, and similarly c epsilon t minus 1 corresponds to the effect of noise at time t minus 1 on yt. Right? But notice that for b epsilon t, it's the effect of noise at time t on y of t. It happens at the same exact time. So this should be a direct effect. So what we're going to do is we're going to let b be equal to 1 under this assumption. Right? So under this assumption, this allows us to rewrite our model in a more meaningful way. And this number c, now since a and b have already been removed or redefined, we're going to be renaming c to be equal to theta 1, corresponding to the parameter associated to one time step in the past, which some people will also refer to as one lag from now. So therefore, our MA1 model is going to be of the form y of t is equal to mu plus epsilon t plus theta 1 epsilon t minus 1. So this is going to be our moving average order 1 process. All right. So epsilon t minus 1 are variables, and mu and theta 1 are going to be some numbers for which we need to find. Now, can I go a higher order than order 1? Obviously, yes. So we can generalize this to what we call a qth order moving process, or moving average process. Moving average process. Right? And this is going to be equal to what? Take a guess of what form this will be. So this will be y of t equals mu plus epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 all the way down to theta q epsilon t minus q. So this is the qth order moving average process for which we will just notate by MA. Right? So now we have the structure for which we want, and now we're going to make our final and most important assumption for MAQ. So assumptions for MAQ, and we've already made this assumption, but I just want to re-emphasize it, is that YT is a stationary process. It's a stationary process. And what do you mean by stationary? Now, there's a formal definition of stationary, and we'll get to this a little bit later, but pretty much it has the same or fixed overall pattern. Pretty much it behaves the same way for all of time t. Right? So two analytical things that is immediately from this, sigma squared t is just equal to sigma squared, and mu t is equal to mu, and these both have to be true for all time t. Right? So the variance of epsilon and the mean of epsilon are all equal to a constant, regardless of when you're dealing with. So now we have our model. So we're going to be, again, just focusing on MA1's calculation today, which, again, is just y of t is equal to mu plus epsilon t plus theta 1 times epsilon t minus 1. So we have these two numbers, mu and theta 1, that we need to approximate, and then we're going to have our model. So let's target the first and easiest one, how to approximate mu, and we're going to approximate it with something called mu hat. We're not going to be using x bar notation, although x bar is commonly used to notate the approximation for mu, but we're not going to be talking about unbiasedness here, and mu technically is a mean of technically some other things, and I don't want those to inflate, so I'm just going to be using hat notation to use approximates, because there's actually several different types of approximates that I want to mention in the near future. Right, so we're going to be approximating mu with mu hat, and the question is, how are we going to do it? Obviously, there's several different ways. Maximum likelihood estimation is one, but today we're going to be just using the method of moments. It's the easiest one to sort of get your head around if you're new at time series. All right, so what are we going to do? So keep in mind the expected value of a y of t is equal to mu. Right? So technically speaking, yt, the random variable, is an unbiased estimator for mu. So that means we can estimate mu with the yk values for all k that are less than or equal to t. Right? That is the observed yk values, and we can use all k less than t, since we're assuming that this model is stationary, right? So we don't have to worry about going too far in the past, because even if it was 50 million years ago, since it's stationary, the model of yt still behaves the same. So the more data, the better for stationary processes. So therefore, if we can use all of the yks and we want an unbiased estimator for mu, one can show that a good estimator via the method of moments will just be equal to 1 over m times the sum from k is equal to 1 to m of yk. It's pretty much an arithmetic mean. And this is going to be true for k less than or equal to t, and m equals the number of observed points, right? And obviously here we're assuming that we have a finite number of points. So here we have an approximation for mu, right? Okay. So that's the first thing that we have. Now keep in mind, since we know the expected value of yt, you should also be able to find the variance of yt as well. We're going to need this in just a moment. So what is that going to be? So that's the variance of mu plus epsilon t plus theta 1 epsilon t minus 1. Constant, variable, independent, we're assuming, so we can distribute this over that addition without having to deal with covariance terms. So we're going to have 0 plus sigma squared, and then plus theta 1 squared times sigma squared, epsilon t minus 1, keep in mind, have the same exact variance. So we have that this is going to be equal to 1 plus theta 1 squared times sigma squared. Right, so this is the variance of y of t. And keep in mind, this is true for all t. And I've seen it so many times, please do not make the mistake and say that this is equal to sigma squared. Sigma squared is for the noise term, not the y term, right? So this is not equal to sigma squared. It's only equal to sigma squared if theta 1 is equal to 0, which rarely ever is the case, right? So we have the variance of yt term. So now the question is, now to approximate theta 1, right? So now let's go through some fancy math. Let's look at the expected value of yt times yt minus 1. So it's the product moment of the thing we're trying to predict today and the thing we had observed yesterday. So what is this? So this is going to be equal to the expected value of, and here's some fancy math. So it's going to be equal to mu plus epsilon t plus theta 1 epsilon t minus 1 times mu plus epsilon t minus 1 plus theta 1 times epsilon t minus 2. And now we need to triple FOIL this and see what that comes out to. So that's the expected value of some fun stuff. So we're going to have mu squared plus mu epsilon t minus 1 plus mu theta 1 epsilon t minus 2. So that's going to be equal to the first phase, mu times mu, epsilon t minus 1, and that last term. And then we can focus on the next phase. That's going to be equal to what? So that's going to be equal to mu epsilon t plus epsilon t minus 1 plus epsilon t theta 1 epsilon t minus 2. That's the second phase. And then the last phase, that's going to be mu theta 1 epsilon t minus 1 plus theta 1 epsilon t minus 1 epsilon t minus 1 again, and then theta 1 epsilon t minus 1, and we're going to have theta 1 squared epsilon t minus 1 epsilon t minus 2. Close brackets, begin the fun. So what do we have here? So the expected value on individual terms is going to be equal to 0 because that's the assumption for our noise terms. So that's going to be equal to 0. This one is going to be equal to 0 for the same exact reason. Here's another lonely little epsilon term that's going to be equal to 0 as well. Do we have any other lonely little residual terms here? Oh, there's a lonely little residual term there, so that goes to 0 as well. Because keep in mind, mu and theta 1 are just constants, so we don't really care about them. And what else do we have here? So let's look at this, these two noise terms. So t and t minus 1, they're independent. So the product moment is going to be equal to 0 for those. There's an epsilon t minus 2. They're different, so they're not correlated. So that's going to be equal to 0. This last term has a t minus 1, t minus 2. They're different, so they're not correlated. So that's going to be equal to 0. And then we're just going to be left with this mu squared and this theta 1 epsilon t minus 1 squared term. Okay, so that's going to be equal to the expected value of mu squared plus theta 1 epsilon t minus 1 squared. Right? Now keep in mind the second moment, or the variance, of a random variable x is equal to the second moment minus the mean squared. So we can actually solve this equation for the second moment of this random variable by adding the mean squared to the variance of both of these expressions. So the expected value of mu squared, we know that's just going to be equal to mu squared, and then we're going to have theta 1 times the expected value of et minus 1 squared, which is just the second moment of et minus 1. So the second moment of et minus 1 is going to be equal to the variance of et minus 1 plus the expected value of et minus 1 squared. So what is this? So we already know the expected value of that is going to be equal to 0, and the variance of et minus 1 is just going to be equal to sigma squared. So as a beautiful and simplified result, the expected value, or the product moment, of yt and yt minus 1 is going to be equal to mu squared plus theta 1 sigma squared. This is the first important theoretical result, and keep in mind this is true for all time t, right? So that's actually very, very beautiful. So what are we going to do with this identity? So we already know the product moment of yt and yt minus 1, and we know everything about yt minus 1. We also know the expected value of yt and yt minus 1. Both of those are equal to mu, so we should be able to find the covariance between yt and yt minus 1, which some people will refer to as the autocovariance between these processes. We'll talk about autocovariance in a little bit more detail later, and also autocorrelation. But technically speaking, the covariance between y and t yt minus 1 from the formulas that we've already established in statistics is going to be equal to the product moment yt minus 1 minus the expected value of yt times the expected value of yt minus 1. That formula holds. We've already proven what the first moment of yt, or the product moment of yt minus 1 is equal to. That's just going to be equal to mu squared plus theta 1 sigma squared. And what is E expected value of yt? Yt minus 1. Both of them are going to be equal to mu, so that's going to be mu squared since it's a stationary process. And notice that the mu squareds will cancel in this expression, and then we're just left with theta 1 times sigma squared for the covariance between them. Once we have the covariance, and keep in mind, covariance is not bounded above nor below and can range from minus infinity to infinity and has very strange units. So for example, if yt is measured in dollars, then covariance is measured in dollars squared or square dollars, whatever that means. So correlation between them is commonly used as an alternative for units because it's bounded between minus 1 and 1. So we're going to be denoting this particular expression as rho 1, sometimes called the autocorrelation, or the first autocorrelation of this process. And this is, again, going to be defined to be equal to the covariance of yt minus 1, all over the standard deviation of yt times the standard deviation of yt minus 1. So we have expressions for the covariance of y of t already. The covariance of yt and yt minus 1 would just be equal to theta 1 times sigma squared. We've already proven that. And the standard deviation of yt will be the square root of its variance of yt. Keep in mind, yt, not epsilon. So that's going to be equal to the square root of 1 plus theta 1 squared times sigma squared times the standard deviation of the other one is the same. 1 plus theta, not sigma, theta 1 squared times sigma squared, and that gives us the correlation. Notice that we have a sigma squared, sigma times sigma on the bottom, so they cancel, and the square roots will eliminate here, just leaving us with 1 plus theta 1 squared on the bottom. So therefore the first autocorrelation for this moving average process of order 1 will be equal to theta 1 all over 1 plus theta 1 squared. Another very important process, and keep in mind this is for moving average order 1. Okay, so keep in mind this is correlation. Sometimes it's easy to approximate correlation of data points in the past. So again, what are we aiming for? We're aiming for theta 1. So if we can approximate rho 1, we have an approximate for theta 1. So that's our goal. So what we're going to do is we're going to approximate rho 1 with rho 1 hat. This is similar to R, the R and R squared value from regression. And this is going to be defined to be equal to the sum. And keep in mind, this is for MA1, and there are equivalent ways for MA2, MA3, and MAQ. But this is going to be the sum from k is equal to 2 to m, so this is previously observed values, of yt minus y bar, and then yt minus 1 minus y bar. So it's looking at the correlation between moving averages. Or between lags, I guess you could say. And that's going to be divided by the sum from k is equal to 1 to m of yk minus y hat. Right? And that's yk and yk minus 1. Right? So this is an approximation to rho 1. So now we have that rho hat 1 will be approximately equal to theta 1 all over 1 plus theta 1 squared. And now we can solve this equation for theta 1. So cross multiplying by the denominator will give us rho 1 hat plus rho hat 1 theta 1 squared is equal to theta 1. And then we can form a quadratic equation from this by isolating and setting equal to 0. So that's going to be equal to rho hat 1 theta 1 squared minus theta 1 plus rho hat 1 is equal to 0. So that's quadratic in theta 1. So we can solve that using the quadratic formula, and we're going to have two values to look at. And keep in mind, we're looking at approximations for theta 1. This is not the exact value because we're approximating rho, right? So therefore, we're going to use theta 1 hat as the approximation for theta 1. And this is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we have two potential values for theta 1's approximate. And keep in mind, this theta hat 1 exists if and only if negative 1/2 is less than or equal to rho hat 1 is less than or equal to 1/2. And this should actually cause you some theoretical concerns, because keep in mind, can't correlation be between -1 and 1? Definitely. So if you get a sample correlation coefficient of your lags to be like 0.78, which is bigger than a half, then this theta hat 1 is not going to have an estimate. So this sample estimate for rho 1 is a requirement for MA1 if you use estimates from moments, right? Because technically speaking, that's the only thing that we have used up to this point. If we use, let's write that a little bit neater, method of moments for mu and theta 1, right? So it does have its limitations, but as long as your approximate is between -1/2 and 1/2, then we have our MA1 model, right? Because once you have your mu and once you have your theta 1 approximates, now you have your model, right? So those are just some of the basics, theory, and also applied side for time series analysis. And now you have your first method for time series predictions. We'll get into simulations and more advanced methods at another time, but I hope you enjoyed this introduction to time series, and I hope to see you in the next video. Take care.